Astronomers have discovered an object so strange that science does not yet have a comfortable name for it. About 71 light-years from Earth, a small red star is orbited by a brown dwarf, an object too massive to be called a planet but too small to shine like a normal star. Now researchers have found strong evidence that this brown dwarf is itself being orbited by a world nearly as massive as Jupiter. It behaves like a moon, looks like a planet, and may represent an entirely new class of object. The system is called CD 30-52722. At its center is a red dwarf containing roughly half the mass of the Sun. Far from that star, at a distance greater than Pluto's average distance from the Sun, travels a brown dwarf known as CD 30-52722b. Brown dwarfs occupy the uncertain territory between planets and stars. They form from collapsing clouds of gas, much like stars, but never become massive enough to sustain the hydrogen fusion that powers ordinary stars. CD 30-52722b has approximately 30 to 37 times the mass of Jupiter, making it much heavier than a planet while remaining far below the mass of a true star. The newly detected object orbits this brown dwarf. Its minimum mass is estimated at about 3/4 the mass of Jupiter, and it appears to complete an orbit every 169 days. Astronomers have cautiously described it as a planetary mass exosatellite. Calling it an exomoon would be tempting. A moon is normally defined by what it orbits rather than by its size. Earth's moon circles a planet, while the planets circle the Sun. In this distant system, however, the central body being orbited is not officially a planet. It is a brown dwarf. That leaves the new object trapped between familiar categories. It may be planet-like in size and composition, but dynamically it behaves like a satellite. The brown dwarf circles the red star, while the Jupiter mass object circles the brown dwarf. The result is a three-level cosmic hierarchy, a giant planet-like satellite orbiting a failed star that is itself orbiting a normal star. The discovery could also represent one of the strongest exomoon detections ever reported. Astronomers have confirmed more than 6,000 planets beyond the solar system, yet no moon outside our system has achieved the same level of confidence. Several candidates have attracted attention, but their signals remain controversial or have disappeared when scientists collected additional data. Exomoons are difficult to find because they are usually much smaller than the planets they orbit. A planet passing in front of its star may block enough light to be detected. A moon produces a much weaker signal, and its changing position around the planet complicates the pattern. Astronomers must separate the influence of the moon from the planet, the star, and the instruments collecting the data. The team studying CD 30-52722b used a different approach. Instead of watching the object pass in front of the distant star, they measured the brown dwarf's radial velocity. This technique looks for tiny changes in the motion of an object as it is pulled toward and away from the observer. An orbiting body does not simply travel around a perfectly stationary host. Both objects revolve around a shared center of mass. Jupiter causes the Sun to make a small motion, just as the Sun causes Jupiter to follow its much larger orbit. If that motion occurs partly along our line of sight, the light from the host shifts slightly toward shorter or longer wavelengths. The researchers used CRIRES+, a high-resolution infrared spectrograph installed on the European Southern Observatory's Very Large Telescope in Chile. Because brown dwarfs are relatively cool and faint in visible light, infrared observations are especially useful for studying them. The team collected spectra of CD 30-52722b and searched for repeated changes in its velocity. They found a strong periodic signal consistent with a companion completing an orbit every 169 days. The companion's gravitational pull appeared to move the brown dwarf back and forth at hundreds of meters per second. The best-fitting model suggested a minimum companion mass of approximately 0.74 Jupiter masses. Its true mass could be higher because radial velocity measurements depend on the angle at which the orbit is viewed. Even at the minimum estimate, this is not remotely similar to a familiar moon. The largest moon in our solar system is Ganymede, which orbits Jupiter. Ganymede is larger than Mercury, but it contains only a tiny fraction of Jupiter's mass. Earth's moon is unusually large compared with Earth, yet Earth is still more than 80 times heavier. In the CD 352722 system, the estimated ratio between the brown dwarf and its satellite is closer to 40 or 50 to 1. That makes the pairing more balanced than most Planet 10 moon systems we know. It begins to resemble a miniature version of a binary system, where two substantial bodies orbit one another. The data may contain another surprise. The researchers found weaker evidence for a second satellite closer to the brown dwarf. This possible object could have around 0.28 Jupiter masses and complete an orbit in approximately 87 days. The two potential orbital periods are close to a ratio of 2 to 1. For roughly every orbit made by the outer satellite, the inner candidate would complete about 2. This arrangement is known as an orbital resonance. Resonances are common in our solar system. Jupiter's moons Io, Europa and Ganymede are locked into a precise gravitational rhythm. For every orbit completed by Ganymede, Europa travels around Jupiter twice and Io completes 4 orbits. Their repeated gravitational interactions help maintain their orbital structure and generate internal heating. If both objects around CD 352722b are confirmed, their near 2-to-1 relationship could provide another clue that the signals come from real satellites rather than measurement errors. However, the evidence for the smaller object is less certain, and further observations are required. The most difficult question is how such a system formed. Ordinary moons are thought to arise in several ways. Some form from disks of gas and dust surrounding young planets. Others are captured objects that pass close enough to become gravitationally trapped. Large impacts can also produce rings of debris that later combine into moons, as may have happened around Earth. A Jupiter-mass satellite would require an enormous amount of material. If it formed inside a disk surrounding the brown dwarf, that disk must have been far more massive than the structures that created the moons of our giant planets. The system is young, perhaps between 50 million and 200 million years old. CD 352722b may have formed directly from the same collapsing cloud that produced the central star. A disk could then have developed around the brown dwarf, creating one or more large satellite objects. Another possibility is gravitational capture. The satellite may have formed independently and later been trapped by the brown dwarf. Capturing such a massive object is difficult because energy must be removed from the encounter. Interactions with gas, the central star or another body might have made it possible during the system's chaotic early history. It is also possible that the pair formed more like a binary. The brown dwarf and the Jupiter-mass object could have emerged through fragmentation of the same collapsing region, with the heavier body becoming the primary and the lighter one settling into orbit around it. In that case, calling the smaller object a moon might hide more than it explains. This is why the discovery has created a classification problem. Our familiar words were developed by studying the solar system. Here, stars dominate the center, planets orbit stars, and comparatively small moons orbit planets. Nature is not required to follow that arrangement elsewhere. A body can resemble a planet because of its mass and atmospheric composition while behaving like a moon because of its orbit. Brown dwarfs make the boundary even less clear because they form like stars but can resemble giant planets. The discovery has not yet produced a direct image of the satellite. The evidence comes from the gravitational effect it appears to have on the brown dwarf. Additional radial velocity measurements will test whether the signal repeats exactly as predicted. Astronomers may also use astrometry, which measures tiny changes in an object's position across the sky. If the brown dwarf is genuinely orbiting a shared center of mass with a massive satellite, precision instruments should eventually detect its sideways motion. Future telescopes may be able to separate the light of the two objects. The extremely large telescope now under construction in Chile will have a main mirror almost 39 meters wide. Its resolution and light-gathering power could allow astronomers to study systems that current observatories cannot distinguish clearly. Confirmation would open a new chapter in planetary science. Moons preserve evidence about how their host systems formed and evolved. Their masses, orbits, and chemical compositions can reveal whether they grew from disks, survived violent collisions, or were captured during gravitational encounters. Exomoons could also expand the search for habitable environments. In our solar system, some of the most promising places for life are not planets. Europa and Enceladus contain oceans beneath their frozen surfaces, while Titan has a thick atmosphere and complex organic chemistry. The object around CD 352722b is probably a hot gas giant rather than a habitable world. But proving that satellites can be detected through radial velocity would give astronomers a new method for finding smaller examples in the future. The most important part of this discovery may therefore be the technique. The same radial velocity method that revealed the first planets around Sun-like stars is now being applied directly to brown dwarfs. Instead of measuring how a planet pulls on a star, researchers measured how a possible moon pulls on a substellar object. 30 years ago, exoplanets seemed exotic. Today they are known to be common. Exomoons may be entering the same transition. The first convincing examples could look nothing like the moons scientists originally expected. CD 352722 may contain a star, a failed star and a planet-sized moon arranged inside one gravitational system. It challenges the categories that make our solar system appear orderly and suggests that nature can construct hierarchies far stranger than anything orbiting the sun. Astronomers may have found the first strong example of a moon beyond our solar system, or they may have discovered something for which the word moon is no longer enough.